Hello and welcome to my YouTube channel. Today we'll be talking about operational amplifiers. These are similar to any kind of amplifier. And we talked about transistors, and you can use them to amplify signals. So transistors too can be classified amplifiers. But we have another device which we refer to as an operational amplifier. When it comes to operational amplifier, these are amplifiers designed to perform mathematical operations, right? That was the initial intended purpose when it comes to operational amplifiers. But nowadays, we can use them to perform other activities other than mathematical operation. We can use them to convert AC to DC, and then from DC back to DC AC. So we can use them in power conversions as well. Now, when it comes to an operational amplifier, right, we can talk about the characteristics, right, that makes up an operational amplifier. We can talk about the distinct properties that ensures that we can really classify a device or consider a device to be an operational amplifier. So first, we look at the electrical symbol of an operational amplifier. And as you can clearly see here, it's kind of a diamond shape. Then we have 5 kind of terminals. All right, we have 5 terminals that showed here. We have, for example, we have 2 input terminals. We have the inverting input and the non-inverting input, right? 2 input terminals. Then when it comes to the output terminal, we have, when it comes to the output terminals, we have only one, right? We just have only one output terminal, which we call an output terminal regard. And we have voltage, all right? We have positive voltage and negative voltage. But when it comes to the design of operational amplifier, we will focusing on the 3 common terminals of an operational amplifier, and they are the 2 input terminals consisting of inverted input and non-inverting input, and then we have the output terminal as well. So these are the 3 main terminals that I will be using to design an operational amplifier, so that we can use it for any intended purpose, whether we want to do addition, subtraction, all the way to inverting or amplifying a signal. Now, as we can see here, so if we're having 2 terminals, that means we can get what we refer to as what? Differential inputs, right? Differential inputs. And when it comes to an operational amplifier, the inputs to the operational amplifiers are mainly going to be what? They are mainly going to be voltage sources. So if I have a terminal, inverting terminal input, we can supply voltage source to that terminal as well as a non-inverting input. So they are going to be receiving only positive, voltage sources, and the output in that situation is also going to be a voltage output. So the signal here is going to be a voltage signal when you come to an operational amplifier. That's the signal that we are going to use. You see? So we have the differential input. Then we have our output voltage, right? So we have differential input voltage, and then we have output voltage as well. Then we can talk about some of the characteristics of an operational amplifier. They tend to have high input impedance. And when it comes to this, all right, this is to ensure that we want to make sure that there's not that much current entering the operational amplifier, right? So in order to ensure a low amount of current or almost zero current in that situation, we make sure that the input impedance, which is impedance here, we can consider to be the same as resistance. So we make sure that the input resistance is very high, and in that process, that will ensure that you have small amount of current or maybe zero current passing through the operational amplifier. Then we have higher voltage gain. Or we have, for example, open low voltage gain. And similar to any gain, right? Anytime we talk about gain, for example, when it comes to amplification, we want to make sure that the gain is very large, right? So again, you can think about a microphone. So if the gain of the microphone is very large and you are speaking very slowly, or maybe you are speaking with a very low voice, but if the amplification gain of the microphone is very large, you can see that that is still going to be amplified and people can hear the voice. So when it comes to any kind of gain at all, it's always good to have what? A high voltage gain. So similarly, when it comes to an operational amplifier, one of the characteristics is that we should make sure that it's having a very high voltage gain. That will ensure that you can what? Amplify any small or weak signal. Then we have low output impedance, right? Which is the same as low output resistance. So you can see here from this diagram, you can see here is ZO. ZO stands for open output impedance. So with the output impedance, we want to ensure that, all right, that impedance doesn't corrupt or affect the voltage output, because the voltage output, or say the output terminal is connected to the output impedance or output resistance. So why do we want this to be the case? Is because if this output impedance, let's say, is very small in that regard, that means since it's connected, meaning in a way it's kind of in series with the output signal. Or if that resistance is very small, it's not going to have much impact on that output signal in that process. So we want to make sure that we have low output impedance when it comes to an operational amplifier. Then we can look at an ideal situation for an operational amplifier. And we talk about the fact that in general terms, when it comes to the characteristics of an operational amplifier, we talk about for that it will have a very high input impedance. So in an ideal situation, we want this thing to be so big that it's infinite, right? So we have the input resistance, which is the same as input impedance to infinite, meaning it's very large, very big number. Then when it comes to the output, the voltage gain is also infinite, right? So it's so large and it's so big. Then for the case of the output impedance, in an ideal situation, one needs to be almost zero, right? To be zero. The output resistance should be zero. And we have also now a perfect balance. So in order for us to have an infinite output, infinite open loop voltage gain, that means we have to make sure that the differential voltage, which is VT, is zero. Why? Because the open loop voltage gain is going to be equals to output voltage over the differential input voltage. Because this is the this is based on following the standard formula for calculating gain, right? When you have you ask to calculate any gain at all, right? So you think about having a box, right? So if I have maybe this kind of example of a box, if you have a box, you look at the input signal or the inputs into that very box, and then you look at what is going on, which is going to be your output signal. So the gain of the block, or let's say any system in that case, is going to be equals to what is going out is your output over what is going in. So gain is always going to be equals to what? Output over meaning output signal over input signal. So in the case of an operational amplifier, so we have our output signal being what? Voltage. And the input to this is going to be what? Bear in mind, we have two input terminals, inverting and non-inverting. So we take that differential voltage, mean the difference between that voltage. That becomes our input into the operational amplifier, and the open loop voltage gain is going to have output over the differential voltage. And in order for us to get an infinite open loop voltage gain, that means we can only achieve that if the differential voltage is equal to zero. And so if it were to be equal to zero, that means V2 has to be equal to V1. So that means that inputs into the two input terminal that we have, they are the same voltage, right? The voltage is at the so V2 is equal to what? V1. As you can see, differential voltage is always going to equal to what? V2 minus V1. So if they are both the same, then you get the differential voltage to be equal to zero, and then you have an infinite open loop voltage gain. Then that is what we refer to as having a perfect balance. So when the output voltage is zero, in that case, then you have V2 being equals to V1, and you have also zero drift, right? So zero drift here has to, it's about how environmental changes can affect the performance of the operational amplifier. And the operation is not really affected by, let's say, temperature or humidity or any other environmental factor. Hence, that means that operational amplifier or the operation of this situation is considered to have a zero drift. So zero drift simply means it's not affected by environmental factors. We have zero drift. And these are some of the characteristics of an operational amplifier. And when it comes to a practical operational amplifier, they share the same characteristics as that of general characteristics of an operational amplifier. But when it comes to an ideal operational amplifier, they differ a bit in that situation. So we talk about the next parameters in the next this video. Bye-bye.